Welcome to Mrs. Miller's notes for her pre-calculus class. These are the notes for section 14.3 entitled Binomial Probability. And today we're going to talk about binomial probability and then binomial distribution. So let's say that a coin is weighted so that the probability of heads is 0.6 instead of being 0.5. So what's the probability of getting exactly 2 heads in 5 tosses of the coin? So here we have an unfair situation where it's not equally likely that both of these events are going to happen. So when you want to flip the coin and get heads, you're going to have 0.6 and 0.6. Anytime you get tails, that's going to be 0.4, 0.4, 0.4. Okay, so if we want to get 2 out of the 5 to be heads, we could have the first 2 be heads and the last 3 be tails. And so there you've got the 0.06 to the second and the 0.04 to the third. But really the heads and the tails could be in any order. They don't have to be in this order. They just have to somehow get a total of 2 heads and a total of 3 tails. So we could have tails, heads, tails, tails, heads, okay? Plus a variety of other different combinations. But again, this has 2 heads and 3 tails. So we have the 0.6 squared and then the 0.4 to the third. So we have a lot of different combinations that can get us the same successful outcome. So this is what is considered a binomial probability. So in order to get rid of all of those extra combinations that are the same, we need to do a combination in our calculations. So if we want 2 of the 5 tosses to be heads, then we have to do a combination 5, 2. So we have to do 5 combination 2. And then we have to multiply it by the probability of getting the 2 heads and the probability of getting the 3 tails. So this would be our calculation that we have to do. Okay, so this is what's called a binomial experiment. And the key for this, the key terminology that they're going to be using is successes and failures. So it might be worded with those actual words, success and failure, or it might say this is what you want, or this is the favorable outcome, but you have to think of it in terms of success and failure. Okay. So when we're doing our calculation here, this is what we'll be using. Okay. So in our example, getting a heads was the success and then getting the tails was the failure. So we're going to do that combination of our success and failure, and then we'll have our first event to the r power, and then we'll have 1 minus the first event. So that's the complement. So you have the probability, and then you have the complement, and then you have that to the n minus r power. Right? So this makes a little bit more sense when we actually do an example. So let's take a look at a few examples here. A fair die is rolled 10 times, and we want to find the probability of each event. Now, this can be done with fair dice, or it can be done with weighted dice. Okay, the example we were talking about was weighted coins. That just helped us get the probability, the 0.6 or the 0.4. But we can still write that as a fraction, okay? So here we want to find the probability of rolling exactly 2 6s. So that's the success that we want, exactly 2 6s. So that means we're going to have, out of the 10 times, we're going to have 2 options, okay? So the probability of rolling a 6 is 1 out of 6 if you're rolling a die. And that's what we want, and we want it twice because we want to roll 2 of them. But we also have 5 out of 6 times where that'll be our failure. And that failure is going to happen 8 times. So then we have to calculate each of these and multiply them together. So the 10 combination 2 is going to end up being 45. The 1/6 squared, that's 1 over 36. And then the 5 over 6 to the 8th power, that is best written as a decimal, 0.233. And we're going to multiply these all together anyway, so it's probably best to write our answer as a decimal, 0.291. So about a 29% chance of that happening. So not very likely, but it could happen. If you rolled the dice twice, rolled the die twice, you could get 2 6s in a row. Now part B is going to change the wording a little bit. It's going to say that we want at most 1 6. So that key phrase right there, at most, means that when we roll, we could have no 6s or we could have 1 6. So we really have two options here. So we could have this or this. So that means we're going to have find the probability of getting a 0, and then we're going to have to add it to the probability of getting exactly 1 6. So how we're going to do that is we're going to have to deal with our combinations here. We're going to have 10 times that we roll it, and we don't want any 6s if we're dealing with rolling 0 6s. So then we'll have the probability of rolling a 6, which is 1/6, but we don't want that to happen at all, actually. So we're going to raise that to the 0 power. And then the probability of not rolling a 6 is 5 out of 6, and we want that to happen 10 times. So notice here that the 1/6 and the 5/6, they have to add up to 1, and that the 0 is the same as the right side of the C, and the 10 is the same as the left side of the C. Okay? And that's following our pattern here with our N and R. Okay? Now, we also have to finish this problem. We have to add this to the probability of finding or rolling 1 6. So there we're going to have 10 times, but we're just going to roll it once. So 10 combination 1. And then again, 1/6 to the first power and 5/6 now to the 9th power. So these are our successes that will have 1 time. Our failures will happen 9 times. So when we do the 10 combination 0, the 1/6 to the 0 power, that's going to be a 1, and then the 5/6 to the 10th power, and we multiply those together, you should get 0.1615. And then the 10 combination 1 and the 1/6 to the first power, that's just 1/6, and then the 5/6 to the 9th power, when you multiply those all together, you should get 0.3230. So when we add those together, we'll get a 0.485. So 48.5%. So that could happen. That's almost a 50-50 chance that that could happen, that you could roll at least 1 6. Okay. And then our last one here, the probability of rolling at least 2 6s. Now the key phrase here is at least. Up above, we had the calculation where we found exactly 2 6s. So if we want at least 2, that means we could have 2 or 3 or 4 or 5, so on and so on and so on, all the way up till 10. So I don't want to do all those calculations. So this is where I'm going to use my complement. Okay? So if I find rolling exactly 2 6s, I can subtract that. Oh, sorry. I want to use part B as my complement, sorry. Because I want to roll either a 0 or a 1 would be the opposite of this. So I would roll 0 or 1 6s. That would be the opposite of rolling 2 or 3 or 4 or 5 and so on. So I'm going to take 1 minus the answer that I got from part B, 0.485. And then that will get me 0.515. So there I'm using my complement to make that work a lot faster to calculate. Okay. because it's way more complicated to find the probability of rolling a 2 or a 3 or a 4 or a 5 all the way up through 10 when I can do the opposite of that and find what it is to roll 0 or 1, which I did in Part B, and then just subtract that from 1, 100%, and I'll find my probability. Okay, so use your previous knowledge from other sections to carry over into these examples as well. That complement we talked about in the previous sections. So now we're going to talk about the binomial distribution. And this is basically just where you can make a table and a graph to show the distribution of your outcomes. So this is how we can describe that how the probabilities of an experiment are distributed among the certain outcomes. So we'll have to make a table of values like it says here. And then the function that assigns each outcome to its corresponding probability is called the probability distribution. So if you hear that phrase, just know what that means. And then we're going to make a bar graph of a probability distribution. And that is actually just going to be called a histogram. And histograms are like bar graphs, except every bar is the same width, and they're right next to each other. There's no spaces between them. And the only thing that can vary with them is their height. Okay, so we're going to take a look at both of these concepts in our next example here. So we're going to make a probability distribution for the experiment of rolling a fair die and observing the number of outcomes, the number of dots. Okay. So here we're just rolling the die and seeing what the outcome is. So when we make our table, we'll have our outcome, and then we'll have our probability. So the outcomes are that we could roll a 1, 2, 3, 4, 5, or 6. And the probability of that, if it's a fair die, would be 1 out of 6 for each of them. Okay, so not a super challenging distribution here. And when we make our histogram, this isn't a very challenging histogram either, but it's just giving you the basics of how to make a histogram. Okay? So we have our 1, 2, 3, 4, 5, 6. These are our outcomes. We can roll. So this is the outcome. That would be the number on the die, the number that would show up. And then over here, this would be our probability that we calculated from the table of values here. So this is going to be 1/6. Now when I make my bars, they'll go up to that probability and over. And my next one's going to go up and over. And I want to try and make my bars all the same size. So if you want to use graph paper, you can. Mine look a little bit off because I'm drawing it by hand. But you get the idea that every single one is the same width, and the only thing that varies in them is the height. And we want them all to be touching. We want them all right next to each other. And the book does a nicer job of making that graph look nice and neat there. But you can see that they have their table here with the probability distribution. And then here is their histogram, or their probability histogram, and every bar is exactly the same. Now when that happens, when every bar is the same, that's called uniform distribution. Well, that makes sense. They're all the same. They're uniform. Okay. Now you can have that, or you can have a binomial distribution as well. This is where the height of the bars is going to change. Now the binomial distribution, that's just like the binomial probability that we were talking about in the previous example. So when we're dealing with this example, we'll have to make sure that we're doing that calculation for the binomial probability. So we have a fair coin that's tossed 8 times, and the number of heads is observed. So this is the key phrase right here. The number of heads is observed. That's our success. It's supposed to say success. S-U-C-C-E-S-S. There we go. Everything else would be failures. Okay, so anytime we roll a head, that's a success. Failure, we're not counting it. So we want to make a table of the probability distribution and then draw the histogram. And then identify what number of heads is most likely to show up. So we have to answer an actual question here afterwards. Okay. Now, doing this table is going to be a little bit tedious because we have to do those binomial probability calculations. So we'll still set it up with our outcomes. And then remember that the outcome is actually the number of heads that we want. And then we'll have our probability of that event happening. So we're flipping the coin 8 times, so we could have 0, 1, 2, 3, 4, 5, 6, 7, or 8 heads. And you could flip a coin 8 times in a row and get all of them to be heads. Now, when we're finding our probability, though, again, we want successes. We want the number of heads. So if I'm flipping a coin and I have to flip it 8 times, 0 of them end up being heads, means that I'm going to do, let's see, 1 out of 2 to the 0 power, and then 1 out of 2 to the 8th. Now, lucky for us that this is flipping a coin, and when you flip a coin, that's a fair coin. It's always 1 out of 2, 50-50. And when you calculate this all out, you get 1 over 256. Okay. And then for getting 1 head, we'd have to do 8 combination 1, and then 1/2 to the 1st power, and 1/2 to the 7th power for our failures. So this is going to be 8 out of 256. And then we would keep going. We would do 8 combination 2, 1/2, 2, and then 1/2 to the 6th. So we want our successes and our failures. And this is going to be 28 out of 256. Okay. So I'm not going to go through each and every one of these, but your book does a really good job of making a table for this. So we'll just take a peek at that. Okay, so here again, they explain how we have to calculate our binomial probability. So we have the combination, we have our successes and our failures. Okay. So here is the chart that they made. So we have the 1 out of 256, just like we calculated, the 8 out of 256, and then the 28 out of 256. It's kind of hard to see, but then it goes up to 56, and then 70, and then it goes back down, 56, 28, 8, and 1. So the pattern does repeat. And then when we make our histogram, again, across the bottom, we want the number of heads. We want 1 through 8. And then we can choose how we want to make our units for the probability. But we have to go from 1 out of 256 all the way up to 70 out of 256. Okay, so mark somehow off to the side. They have a couple measurements here just for reference. If you wanted to, go every 10 or every 35, that would be okay. It's probably good to use a value that's in the table. Here they have 28 out of 56, so we can tell what that height is. Okay, but then for your, we have an outcome of 0, so 0 has to go up to 1. Now notice that 0 starts on that axis, so the bar for 0 is going to overlap a little bit with that axis. Okay, and then this is 1. This is your first outcome of getting 1 head. Okay, well, it's really your second outcome, but it's the outcome of getting 1 head. Okay, and then we have 2, and then 3, 4, and then the pattern repeats and goes back down. Okay, so now the bars are different heights. They're, again, the same width, and they're all right next to each other, but they're different heights. So the one that's the highest then, right here, this one, 70 out of 5, or 256, that's for 4 heads. Okay, so 4 is going to be the most likely. Okay, so you'll have to do this by hand. I'm just trying to save a little bit of time by showing you the book version since it's a lot nicer and neater. I'm sure you can draw your axes and you can label and choose your units, but just pay attention. If you have 0, 0 is on that axis. I don't think we saw that in that other histogram because we were starting with 1, so 0 was blank. That's why we were scooted over a little bit there. We had that space. Okay, but here 0 was one of our actual outcomes. So that's going to overlap there. Okay, so this section is a little bit trickier just because you have to think about the binomial probability in terms of successes and failures. So again, read these problems carefully. Setting them up and doing the calculations isn't that bad, especially since you know they're binomial. But remember, on a quiz and a test, you're going to have to know the difference between this section's material and other sections' material. So really pay attention to the wording. And they're all odds, so you can check them in the back of the book. Solutions are worked out on the class website. And if you have questions, come on in and see me before school.